Section 6.8, Lagrange's method. We're going to do a couple of very easy examples. To remind you, Lagrange's method is where we trying to find the extreme value of a certain function f, x, y, z under the constraint such that g, x, y, z has to be equal to k. Now, under that constraint, there is sometimes, not always, that we can find the maximum or the minimum value that we need. So the Lagrange's method states that what you do in order to hunt down this extreme value is you set u equal to the f plus lambda g. And then you will set partial u, partial x equal to 0, y, and z all equal to 0, which will give you a total of 4 equations, 1, 2, 3, 4. And out of these 4 equations, you are going to be able to come up with some solve for x, y, z, and lambda. And by the time you're done, you will have a bunch of values, and some of them will be your extreme value. Now, as an example of that, let's look at this super easy example. G is the condition x over a plus y over b plus z over c equal to 1. And we're supposed to find out the maximum value we can get out of x, y, z. You can consider that to be the volume, but we really don't care what it's called. Let's just crank it out according to Lagrange's method. So to do that, we'll follow exactly what Lagrange says. We'll set u equal to f, which is just x, y, z, plus lambda times g. And g is this stuff, which is x over a plus y over b plus z over c. Now, and then the next step, we take all 3 partials. So partial u, partial x. With respect to x, then we get y, z. So y and z are both constants for this one. And then lambda divided by 8, since y and z are both constants. Similarly, and this is set to 0. Similarly, partial u, partial y is equal to xc plus y is lambda over b. See, you can see there's a pattern emerging. Everything is identical. So that's the beauty of the Lagrange method. Then partial u, partial c equal to xy plus lambda over c. You can just copy it out of the others. Anyway, so we have these 3 equations. And as we did in the earlier example, we'll do this multiplying trick. Well, multiply was missing. We want x, y, z, kind of. And anyway, it has only y, z. So multiply this equation by x, this equation by y, this equation by z, and then add everything up. If you do that, then we have, adding everything, we have 3xyz plus lambda times x over a plus y over b plus z over c, and that equal to 0. Okay, so I've done the multiplication and addition, and which this thing right here, as given to by the equation right here, this is just 1. So this is 1, which means what we have is that lambda equals to negative 3xyz. All right, and then we will plug this into, well, the first equation right here, partial u, partial x. Then we will have, so then plug this thing in the lambda right here. We have, so partial u, partial x equals to yz plus negative 3xyz divided by a equal to 0. Which means, rewrite this thing, we have yc 1 minus 3 over ax equal to 0. Now, because we're maximizing x, y, z, we don't want any of this stuff to be 0. Y and z cannot be 0, which means this has to be 0. And if this is 0 right here, that means x equal to, you can solve for x equal to a over 3. And similarly, just by symmetry alone, we know that y equal to b over 3 if we go through the same work, and z equal to c over 3. The reason being that we just plugged it into the first one, but everything is symmetrical. And therefore, the volume that we are maximizing is going to be ABC over 3 multiplied multiplied all three together, that would be 27, and that would be our answer. See, it's a very quick and easy problem. We're gonna do yet one more quick and easy problem. It's just to show you that the Lagrange's method is very straightforward if you can solve the four simultaneous equations. However, sometimes the equation is difficult and then it becomes kind of a pain. However, but luckily we are only doing a couple of easy problems, so we're gonna come out looking pretty good. So let's say we have a triangle. Okay, the question is, given any triangle, we want to maximize this particular function. So what we're trying to maximize is this thing, sine x, sine y, sine z, where x, y, z is the angles inside a triangle. I will draw it right here. Okay, so let's say you have a triangle, and this is x, y, and z. So given that is true, what is the constraint? Well, the constraint then is the basic formula of x plus y plus z equal to 180 degrees. That would be our constraint, which is the g value. So how do we maximize this? Well, what we're trying to prove here actually is that for it to be maximized, this has to be an equilateral triangle. That is, x, y, and z has to be the same. Okay, so to prove that, we will use Lagrange's method and follow this particular plan here, which is u equal to first f sine x, sine y, sine z, plus lambda times the constraint, which is x plus y plus z. So as you can see, for Lagrange's method, we just follow the rules and we will get to where we want to be. So next, following the rule, we take partial u, partial x. Taking partial x, so sine x becomes cosine, and the other stuff stay the same because these are constants for x, so it just stays there. Plus, what's this? This thing, derivative with respect to x only, it leaves you just lambda, and you go to 0. As you can see, this thing goes exactly the same way with y. It becomes sine x, cosine y, sine z, plus lambda again. Okay, the lambda doesn't change because of that symmetrical relationship. And then lastly, partial u, partial z equals to sine x, sine y, cosine z, plus lambda. So that's looking pretty good. So then from this, then you have, which means out of this relationship, you can see that this and this and this are going to be the same because all three of them have to be 0, which means that among other things, we will say that, say these two equations are the same. Okay, if these two equations, these two terms, in fact, all three terms are identical because they all add up to be, they all equal to negative lambda just from these equations. So which means they're all the same, they're the same value. And so let's say if the first two are the same, we'll cancel out sine z, which will give us cosine x sine y equal to sine x cosine y. And assuming that nothing is going to be 0 here, we will have sine x. So in other words, sine y divided by cosine y equal to sine x divided by cosine x. And this, of course, is just tangent x, and this is tangent y. And we know that the tangent function, and we're considering from 0 to 180 degrees, the tangent function is a one-to-one function from 0 to 180. So which means that that means x equal to y coming out of this, which means, of course, by the same logic, then y equal to z because everything is symmetrical, and to that means x also equal to z. So the three angles are the same, which means that the triangle has to be either equilateral, which is what we've been trying to prove. Now, in doing this, we have to be careful to state that cosine y cannot be 0, okay, before we can do any of these things. But that can be readily verified because of the angles having to be 180 and such.